Okay, this is podcast 6.3 for chemistry, and we're going to talk about stoichiometry. So, stoichiometry is a way to use a balanced chemical reaction to predict how much of something should be formed. The other ways that we can use stoichiometry is also if we want to produce a certain amount of product, we can also use stoichiometry to figure out how much of the reactants we should put in. The whole idea, though, is that using stoichiometry, you take a balanced chemical reaction and you can manipulate it to kind of tell you what you want to know. It's really a very useful idea and topic, and it's used in the real world all the time. Scientists use stoichiometry to predict how much product should be produced from a chemical reaction. So what they can do is they can tell based on the process that they've developed or the series of steps that they have, they can figure out whether or not their process is working. What is their percent yield? Is there something that's going wrong because they're not producing as much as they expect? So stoichiometry happens all the time in real life. It's something that gets used a lot, especially in the industrial world and the engineering world. But you're probably panicking a little bit because we're talking about using a balanced chemical reaction and then doing math with it. But it's okay, we're going to start simple. We're going to start by making a sandwich with stoichiometry, and then we'll move on to the chemicals. So the first thing with our sandwich stoichiometry is we need to list our ingredients. So the ingredients I have, since we're making a BLT, would be bread, bacon, lettuce, and tomato. And because I'm lazy, and all chemists tend to be lazy, we like to simplify things and give them symbols. These are the symbols we're going to use when we go to write our formula. So here's how you're going to make your perfect BLT sandwich. You're going to take 1 slice of bread, add 3 strips of bacon, 2 slices of tomato, and 1 big leaf of lettuce. And then you're going to top it with a 2nd slice of bread. So what we want to do is write a balanced chemical reaction for what we're doing there. So the first thing I'm going to do is go back to what we said. We said we take 1 slice of bread and then we end it with a slice of bread. So we have 2 pieces of bread, plus we wanted to add 3 strips of bacon, plus 2 tomatoes, 1 big leaf of lettuce, and I'm just going to make an L because we usually don't put ones there in our chemical reactions. And then for the product here, we're just going to take all of this and I'm going to shove it together. But instead of these being coefficients out front, they're now going to become little subscripts. So this will be BD2, BN3, T2, L. So this is kind of a synthesis reaction. We're taking all these things and we're forming one product. So this is our balanced chemical reaction for making a BLT sandwich. And what we're going to do is we're going to use that reaction that we just wrote, and I'm going to write it back up here so we can use it to answer some questions. Nope, that's not right. Let's try again. Okay, so there's the product that we were looking for. So it says, here are some questions for you about making our BLT sandwiches. If I have 10 slices of bread, how many sandwiches can I make? So if we know 2 slices of bread go into each sandwich, if I take 10 divided by 2, we know we're going to be able to make 5 sandwiches. If I have 8 strips of bacon, how many sandwiches can I make? Well, if 3 strips go into each sandwich, then we can make 2 sandwiches. We can only make 2 sandwiches, we can't make 3. In order to make 3, we'd have to have 9 strips of bacon. So in this case, we're only going to be able to make 2 sandwiches and then we'll have some bacon left over. The next question is, what if I have 4 slices of tomato, 6 strips of bacon, and 3 slices of bread? How many sandwiches could I make? Well, if I had 4 slices of tomato, from that balanced reaction that we wrote, and you can see it on the paper that you're taking notes on, we know that we use 2 slices of tomato per sandwich. So from the tomato, we can make 2 sandwiches. Then we have 6 strips of bacon. And from that same balanced reaction, we can see it takes 3 strips of bacon to make each sandwich. So this one will also make 2 sandwiches. And the last one is 3 slices of bread. From the balanced reaction, we need 2 slices of bread for each sandwich. So because I can't make a half a sandwich, this one will only let me make 1. So because I can only make 1 sandwich with the bread and I can make 2 with the other things, this is really the only one that matters because it's the smallest. I only have enough of my smallest ingredient to make 1 sandwich. So how many sandwiches could I make? I could just make 1, or else, because then I'm going to run out of bread. So the next one, how many sandwiches could I make from 630 slices of bacon? So I have 630 bacons, and I have 300 slices of tomato. So we're going to do the same thing. Into each of the sandwiches, there goes 3 strips of bacon. So 630 divided by 3 is 210 sandwiches. And the tomatoes, we go for 2, and this can make 150. So the answer here would be I can make 150 sandwiches because I would run out of tomatoes before I run out of bacon. So would I have anything left over? Well, the tomato's going to get completely used up. I'm not going to have anything left over. I am, however, going to have some bacon left over. And if I want to figure out how much I'm going to have left over, what I do is I can make 150 sandwiches because that's what it said with my tomato. And I know into each of those sandwiches I'm going to put 3 bacons. So 150 times 3 is 450. So I have 450 bacons that are going to be used up making those sandwiches. I had 630 slices. So 630 is what I had. I used 450. So that means with the bacon, I'm going to have 180 strips of bacon left over. All right. Obviously, this is a little easier than using compounds and elements that we use in a balanced reaction, but the idea is going to be the same. So what we're going to do really quick is review how we write balanced chemical reactions from word equations. So what I have here is our first example. We have hydrogen gas, and hydrogen is a diatomic, so it's H2, and it's a gas. And means plus. Oxygen gas. Oxygen is another diatomic, so O2, and it's a gas. To form water, vapor, so H2O vapor makes it a gas. That's writing out all the formulas, then I have to go back and balance. And remember, balancing is where you try to make the same number of elements on both sides of the arrow. So 2 hydrogens here, I have 2 on this side. I only have 1 oxygen on the product side, and I have 2 here. So I'm going to have to put a big number 2 out in front, that coefficient. That changes my oxygens to 2, but it also changes my hydrogens to 4. So the last thing I need to do is come over here and throw a 2 in front of that hydrogen in order to make 4 hydrogens on both sides. So that would be the correctly written balanced chemical reaction for that. The next one we're going to do is lithium metal. Lithium is not a diatomic, but they're telling me it's a metal, so I'm going to say S. Reacts with magnesium chlorate. Magnesium has a +2 charge, chlorate has a -1, and I need 2 of those. I know this is aqueous because they're telling me it's a single replacement reaction. So what you would have to do is you'd have to look on that laminated yellow sheet at the activity series, and you'd look to make sure lithium is higher up than magnesium, and it is. Lithium is the most reactive metal. So this reaction will happen, and this is where the lithium comes in and joins with the chlorate, and the magnesium gets left out by itself. So the magnesium goes by itself, and then the lithium chlorate is our other product. And that's aqueous because it's the compound. So I have a lithium here, a lithium there, those are balanced. 1 Mg, 1 Mg, and then I have 2 chlorates right here, and I only have 1 chlorate here. So I need to put a 2 in front of the lithium chlorate, and that changes my lithiums to 2 though as well, so I have to put a 2 there. That would be the correctly balanced chemical reaction. All right, we're going to use the first one that we wrote, the formation of water reaction. So it says, This is the one, and what we have right here is just an illustration, a picture of what you're seeing. So we have 2 hydrogen molecules. Here's your 2 hydrogen molecules, 1 oxygen molecule, and then it forms 2 water molecules, and there's your 2 individual water molecules. What do the little numbers, which are called the subscripts, tell you? So these little numbers right here, they tell you how many. They tell you how many you have. So that's the first part. The next part is, what do the big numbers, which we call the coefficients out in front of the compounds, tell us? So right there, those also tell us how many, but kind of in different terms. The little 2 is saying we have 2 hydrogens. The big 2 out in front is saying we have 2 of this entire thing. So the coefficients also tell us how many, but they tell us how many molecules, how many atoms, they tell us how many particles we have. And I want to kind of fit that in there. So they tell us how many particles. These tell us how many atoms you have. Okay, coefficients are what we just talked about, and when we're looking at these balanced chemical equations, the coefficients represent 3 different things. And those things are moles, and that's the most common use of those. They're molecules, atoms, or formula units, or particles, and that's what we just talked about. And those coefficients can also represent liters. One thing that coefficients do not represent is grams. So it's important when you see these reactions, like this one, what this is not saying is that 2 grams of hydrogen react with 1 gram of oxygen to give you 2 grams of water. That is not correct. This is saying 2 moles of hydrogen react with 1 mole of oxygen to give you 2 moles of water. It's also saying 2 molecules of hydrogen react with 1 molecule of oxygen to give you 2 molecules of water. So it's really, really important that you understand that those coefficients are not grams. They can be moles, they can be particles, but they cannot be grams. So using that balanced chemical equation that we just wrote down, we want to try these problems using the formation of water. So it says, if I have 4 molecules of hydrogen, how many molecules of water could I form? Well, we can set it up in a quick little table. So I have 4 molecules of hydrogen. From the balanced equation, I know that for every 2 moles of hydrogen that go in, I get 2 moles of water to be produced. And then your answer would be, well, we'll put it there, 4. And that should make sense looking at this. Since 2 and 2 are the same number, if I change this to a 4, this would also have to change to a 4, so they're equal quantities. If I have 8 molecules of oxygen, so if I put an 8 here, I have to multiply everything else by 8 because that's what I just increased it by. And this is always half of what the water would be. So when this is 1, this is 2. If this were 2, the water would be 4. If this were 3, the water would be 6. But since it's 8, if I put an 8 in front of here, then this is going to be 16. It's going to be double the amount. 6 liters of water. So if I had 6 liters of water, I would have half the number of liters of oxygen because that 8 is no longer there. It's back to a 1. So if I made this 6, I would have to make this 3 because the oxygen is always half as much as the water. The next ones we have here, 4 molecules of both oxygen and hydrogen. Well, if I had 4 molecules of hydrogen, I would produce 4 molecules of water. So the hydrogen will give me 4 waters. We'll write it this way. 4 hydrogens will give me 4 waters. If I had 4 oxygens, then I'm going to produce double that for the water. So I'm going to produce 8 waters. This question is saying I have 4 of both of these. Even though I could produce 8 waters with the oxygen, I only have enough hydrogen to produce 4 waters. So the answer for this one would be 4 molecules of water. I have 3 moles of oxygen, so if I changed this to a 3, then my water would be 6. And the last one is 4 moles of hydrogen gives you, or needs how many moles of oxygen to react with. So if this was 4, it reacts with half the number, which would be 2 for the oxygens. So you can do those ratios using the coefficients in the balanced reaction to figure out these ratios that we're looking at here. All right, here is the diagram. And what we've been working on up to this point is right here. We've been staying in the same substance. So grams of A, we would go to moles of A using the molar mass, and then we use Avogadro's number to go to particles of A. We are adding on to this because stoichiometry is about being able to move around the reaction, going from reactant to product, getting everywhere in there and using all those substances. So how this is different is now I have moles of A, so it's kind of split in half. These are all your starting, this would be your starting substance, whatever it is, and B is your ending substance, it's where you're trying to get to. So if we were looking back at that reaction that we just answered all those questions with, if I wanted to know if I put 2 moles of hydrogen in, how much oxygen would it need to react with? Hydrogen would be my A, oxygen would be my B. It's what I'm going to. I'm starting in hydrogen, I'm going to oxygen. So this is my A, this is my B. So we've expanded what we're doing here. The liters of A and the liters of B, we're going to get to that later on. We're not going to talk about that right now. So when you see this diagram from now on, I'm going to cut this bottom part off because we're not going to use it right now. So don't worry about that. This right here down the middle is the most common pathway that you're going to take. You're going to go from grams of A, use the molar mass to find moles of A. Then you're going to use those coefficients in the balanced equation to get to moles of B, and then you're going to use the molar mass to go back to grams of B. And this may seem a little overwhelming right now, but we're going to get lots of practice with this. So, some vocabulary from that diagram. Reactant wasn't on there, but you should know that that's what you start with. The product is what you make. Molar mass is the mass from the periodic table. You should know that. That's your grams per mole. PV equals nRT is the ideal gas law. We're going to talk about that later on when we talk about gases. When it says balanced reaction in the diagram, you're going to use the coefficients. That's what it's talking about. Use the ratio of the big numbers out in front. And then Avogadro's number, of course, is the 6.02 times 10 to the 23rd. So we're just going to do 4 practice problems here on the podcast together, and then we'll do more in class. So the first one says, how many grams of water can I make from 25 grams of hydrogen and an excess of oxygen? The reason they're telling you that there is an excess of oxygen is they're saying we have enough oxygen, we don't need any more. This is going to be what limits the reaction. It's what you should base your stoichiometry off of. So what I like to do when I'm doing these is it's saying how many grams of water. So I like to go here and I'm looking for grams. So I would put like a question mark with grams underneath the water so I know that's where I need to go. And they're saying I have 25 grams of hydrogen to start with. So under the hydrogen I would put 25 grams. So I'm starting here and I need to end up in grams of water. So if I look at the diagram, my grams of A is my hydrogen. It's where I'm starting. And I'm going to work my way all the way to grams of B. And grams of B is the water. So I need to go from grams of A to grams of B. And you can see right now that this is going to take 3 different conversions. It's going to do the molar mass, balanced reaction, and then we're going to do molar mass again. So these are going to get a little longer with their setup. You still always start with what you're given in the problem. So in this one, I'm going to start with 25 grams of hydrogen. It's really important now that we're doing stoichiometry that you list what the compound is so you can keep track of where you're at. So I'm going to put 25 grams of hydrogen. The first thing it tells me to do is the molar mass. So if I looked up hydrogen's molar mass on the periodic table, it would be 2 grams per 1 mole. So I'm going to plug that in as my first conversion factor. If I'm in grams, I have to divide by the molar mass. So 2 grams is 1 mole, and those are both of hydrogen. So that takes care of that step. My next step is to go and use the balanced reaction, like we were doing when we made the sandwiches. So I would use the numbers that are out in front here. For every 2 moles of hydrogen that I put in, and I put that down there because I need my moles of hydrogen to cancel. I'm trying to get to the water, so that's what I put on top. I have 2 moles of water being produced. This is the step that allows us to change whatever substance we're looking at. So I've gone from grams of hydrogen to moles of hydrogen, from moles of hydrogen to moles of water. Using the balanced reaction is the second step. And then my third conversion factor is molar mass again, but this time I want the molar mass of water. So on the periodic table, if we look up the molar mass of water, we would calculate it as 18. So there's my last conversion factor. This is moles. So this time the 1 mole of water needs to go on the bottom. That way it's going to cancel with that. And then I'm going to put the 18 grams of water on top. That doesn't cancel grams of water. That's what I needed. That's what they asked me for. So when I multiply all that out and I get my answer, it's 225 grams. And it's really important that I write water so that we know that's what I went to and that's what I calculated. So those are your 3 conversions that took care of the 3 steps that we saw in our diagram. Okay, next one. How many grams of oxygen, so I'm looking for grams of oxygen, do I need in order to produce 10 moles of water? So I'm starting with 10 moles of water. So if I look down here, I'm not starting in moles. I'm starting in moles of water, not grams. So I'm not starting here. That's not needed. This is the path I'm taking right here. I'm starting with moles of water, and I'm going to work my way because they're asking me for grams of my second substance, which in this case is oxygen. So this is only going to take 2 steps. I'm going to start with what they gave me, 10 moles of water, and then I look for conversion factors. I can go right to the balanced reaction for my first conversion because I'm already in moles, and that's what these big numbers represent. So for this one, I'm starting in water, so I would put the 2 moles of water from the reaction on the bottom, and I'm going to put the 1, because remember there's a 1 there even though we can't see it, 1 mole of oxygen on top. That takes care of this step right here. The next thing I'm going to do is I'm going to use the molar mass. I want to use the molar mass, though, of what I'm going to, the molar mass of B. So B in this case is oxygen. Oxygen, if I add it up, is 32 grams in 1 mole. That's from the periodic table. So when I go to set this up, my moles of water have gone. I'm in moles of oxygen now. So I need to put the 1 mole of oxygen on the bottom. That way it's going to cancel. And I'm going to put 32 grams of oxygen on top. And they asked me for grams of oxygen. That's what I have left over here. It's not crossed out. So when I do the math, I take 10 times 32 and I divide by 2, and my answer is 160 grams of oxygen. So that one was only 2 conversion factors long. Okay, third problem. How many moles of hydrogen gas will react with 5 moles of oxygen gas? So I'm looking for moles here, and they've given me 5 moles to start with here. So I'm going from oxygen to hydrogen, and I'm starting in moles of oxygen, and I'm wanting to end in moles of hydrogen. So that means I only use the balanced reaction and I'm done. It's just one step from here to here. So I start with what they gave me, which is the 5 moles of oxygen. I'm only going to need one conversion factor. I use the balanced reaction. Since I have oxygen, that's going to go on the bottom down here. So 1 mole of oxygen goes on the bottom, and then 2 moles of hydrogen go on top. And that is it. They didn't say anything about grams. I don't have to do molar masses. That cancels, leaves me with moles of hydrogen, which is what I needed. So 5 times 2 is 10. And that's the end of that problem. So that was a pretty short one. Okay, last problem together. How many grams of hydrogen? So how many grams of hydrogen? That's what I'm looking for. Will be needed to produce 100 grams of water. So I'm starting with 100 grams of water. And I'm trying to find how much hydrogen that will take. So since I'm starting in grams of water, and I'm wanting to work my way all the way to grams of hydrogen. So this one is going to take 3 conversion factors again. We're going to do molar mass, then we're going to do the coefficients, and then we're going to do molar mass again. Starting with 100 grams of water. Because I'm in water, I want to do the molar mass of water first. And we already added that up earlier. It was 18 grams. So there are 18 grams of water in 1 mole of water. I have to get to moles because that's what's represented in the balanced equation with those coefficients. So now that I'm in moles of water, I can say for every 2 moles of water, and I would put that on the bottom so that it cancels with that, I'm trying to get to hydrogen, and there are 2 of those. So 2 moles of hydrogen. And then they didn't ask me for moles of hydrogen, they asked me for grams. So my last step is to do molar mass again, but this time of hydrogen. And hydrogen is 2 grams per 1 mole. That's its molar mass off the periodic table. So since I have moles of hydrogen on top here, the 1 mole of hydrogen needs to go on the bottom, and I'm going to put the 2 grams of hydrogen on the top. These guys are going to cancel. I'm left with grams of hydrogen, which is what I needed. So I multiply everything on top, divide by everything on the bottom, and you end up with 11.1 grams of hydrogen. So when you come to class, we're going to do a lot of practice with this. Make sure you have questions. If you don't have the handout that has this diagram in it, you should go back and take a picture of it. Maybe you could screenshot it with your phone. Whatever you need so that you have this and you can use it until you're comfortable doing it without the diagram. So lots more practice in class. We have labs and activities and worksheets and all sorts of good stuff to do with this. But stoichiometry is something we're going to use through the rest of the year. So there's your intro to it, and we will do more practice in class.